welcome to Imagine RT, and this is our senior design project for our Robo Ornithopter. Wait, hold on. You're probably watching this wondering, what is an ornithopter? Well, let me be the one to describe it to you. An ornithopter is a device that flies using the flapping wings to generate thrust, as opposed to traditional aircrafts that fly using propellers or turbines. Now that that's all cleared up, let's introduce the team. Our team consists of our computer engineer, Sherry Matthews, our electrical engineer, Noah Washington, who is your voice for today's video, then Jack McCabe, Jonathan Dell, Nathan Palmer, and Gladys Wentworth as all of our mechanical engineers on the project. Back in August of 2021, our client, Professor Lampkin Kennard, recruited us to create a flying ornithopter for RIT's robotic zoo. She gave us a few requirements. Our ornithopter must fly in a controlled manner by stabilizing itself laterally and longitudinally. It also has to fly a distance of 100 yards, which is as long as the length of a football field or the Statue of Liberty is tall. Since Professor Lampkin Kennard wanted us to be displayed at Imagine RT in April of 2022, she also wanted it to be able to fly for 15 minutes before needing to be recharged. Dr. Lampkin Kennard also wanted it to be capable of landing, or at least be able to withstand impacts. And as our final requirement, since it will be added to RIT's robotic zoo, she wanted it to resemble an animal. After reviewing these requirements and some careful deliberation, we decided to base our ornithopter after a hawk, more specifically, a red-tailed hawk. We began generating concepts using a morphological system analysis. We then drew out each of the concepts and through the use of some engineering tools called the Pew chart analysis, decided upon this design, which was our second initial concept. As you may have noticed in that concept, the ornithopter needs to have a motor to drive the wings. We decided to use a brushless motor for its large torque-to-rate ratio, but needed to gear it down to obtain our desired speed. To do so, we used a gear ratio of 1 to 94.5. Our greatest challenge was the wings. To make the wings, we started with this top view of a red-tailed hawk, and as you can see, the wings have thicker parts made up of bone and muscle, and the thinner parts which are made up of just a few layers of feathers. We broke each wing into sections and measured the lengths of the thick and thin portions to design an airfoil that is a wing cross-section. After we had the appropriate dimensions, we were faced with the challenge of determining materials. Since our ornithopter isn't an actual bird and we don't have access to feathers, we needed to choose materials that were durable enough to survive a crash, yet light enough to allow for flight. This is a CAD model of our final design for the airfoils. The thick bone and the muscle portion of the wing is made up of balsa wood, while the thin feather portion is made up of flexible carbon fiber rods. The next step was to develop the wing linkages, or how the wings would attach to the body in gears to create a flapping motion. One of the things that made the wing linkages difficult was the need to match the bird movement, and to do so we began with a video of a flying red-tailed hawk that we found online. We then used a software called Tracker to put points on the beak, middle joint, and tip of each wing. The software tracked the movement of those points and created vectors on the X and Y positions. We then imported those vectors into MATLAB to recreate the wing patterns. We then designed, 3D printed, and tested linkage designs until we got the one that fit the pattern. However, the other challenge associated with the wing linkages was to determine what material to make them out of. Like the airfoils, they needed to be lightweight but also able to withstand impacts. It was for this reason that we decided to use carbon fiber rods, with balsa supporting rods mounted on the back of the wing for extra stability. Time to get into the electronics portion of this project. It all starts with our 4-cell LiPo battery, which is roughly 15 volts. We also have this blue module that's called our voltage converter, and that converts our voltage from 14.8 volts as displayed on there, down to 5 volts so that we can power up our Arduino and all of the blue servos that you see in this image. There are some components that weren't shown in that photo, and that includes the brushless motor, our electronic speed controller, our receiver, and our MPU 6050 sensor. We did a lot of testing of the motors to make sure they responded to the remote inputs properly. We also created a control system, which is necessary for ease of flight. Though the ornithopter is controlled using a remote, it also needs to have some internal programming to make it more intuitive and manageable to control. The inputs are sent from the remote control of the transmitter to the receiver, which is then wired to our Arduino Nano microcontroller, which is essentially the brain, where all the signals are processed. The flight system that the ornithopter itself then reacts to the input. All the while, an internal measurement unit, that's the MPU 6050 sensor, sends data about the ornithopter's position back to the brain of the system, so it can be processed to help maintain flight. Our final design put all of these components together to create this ornithopter. Though we didn't have enough time to get it to fly, we believe it would if it were tested enough. We would like to extend our warmest thank yous to our client, donor, and supporter, Dr. Kathleen Lampkin Kennard, our experts in the field at Lockheed Martin, our guide for this whole process, Arthur North, and our sponsor, RIT, along with all of our professors who have helped us obtain the knowledge and skills necessary to build this device.